electron configurations in the periodic table. So valence electrons, as we've mentioned before, we can predict how many valence electrons by what group the element is in. So in terms of electron configurations, valence electrons are the ones in the outermost principal shell, the principal shell with the highest quantum number. In the hotel, this is the electrons staying on the highest floor of the hotel. Okay. These electrons are really important because they are on the outside of the electron, and they are the ones that get involved in chemical bonding. Okay, so we've got the valence electrons, those are the outside layer, and then everything else closer in than that are called the core electrons, because they're inside like the apple core. So if we look at the electron configuration for silicon, 1s2, 2s2, 2p6, 3s2, 3p2. So we look at these numbers, 1, 2, and 3. Those represent the floors of the hotel, the principal shells that have electrons in them, and the highest one is 3. There are 2 subshells here. They both have electrons in them. And so the valence electrons are all of the electrons on the 3rd shell. All of the people staying on the 3rd floor of the hotel. They're in 2 different rooms. That's okay. They're on the 3rd floor. So those are the valence electrons. Everything below that is the core electrons. This corresponds to the group number when you use the 1A, 2A, 3A group numbers. Silicon is in group 4A in the periodic table. It should have 4 valence electrons, and sure enough, it does. Not a coincidence. So let's write an electron configuration for chlorine and identify the valence electrons and the core electrons. Well, how many electrons does chlorine have? 17. And chlorine on the periodic table is in which period? It's in period 3. Which block? The P block. And how far over in that P block? 5 over. So that's its position on the periodic table. So we're going to go up to that. There's different ways you can think about or remember writing these. You can say, okay, well, that's where I'm going to end. I'm just going to fill in everything before that. Or you can count it through on the periodic table, whatever makes the most sense to you. So 1s2, 2s2, 2p6, 3s2, and it's going to end with 3p5. Are you at least feeling like, oh, I kind of see how she did that? So this is the position on the periodic table. So then identify the valence electrons. So we're going to look at these numbers, 1, 2, 3. We're going to find the largest number. And all of the electrons on that level are valence electrons. So those are the valence electrons. How many are there? 7. 7 valence electrons. And the rest of these are core electrons. And there's 10 of those. Three. The highest floor in the hotel. So on the 3rd floor, the S room is full, and the P room has 5 people staying in it. There are a total of 7 people on the 3rd floor. Those are the valence people. This kind of sounds like the village people. Those are the valence people. Everybody else is on the lower floor. So the valence electrons are in the highest occupied shell, so the 3rd shell. All the electrons on that shell. Any other questions? What we observe is that elements in the same column have the same number of electrons, valence electrons, and similar outer electron configurations. So in group 1A, all of these, their electron configurations are going to end with something S1. In group 2A, they all end in something S2. Group 3A, they end in S2P1. Here it's on the second level, here it's on the third. Fluorine and chlorine, their electron configurations end with S2P5. That is why fluorine and chlorine share many of the same chemical properties. They have the same number of valence electrons, and it's the valence electrons that have a lot to do with the reactivity of an element. Over here, neon and argon both have 8 valence electrons. Helium is up here, being the bratty little brother. Helium is over here because its only room is full. It doesn't have 8 valence electrons. But on that first floor, there's not room for 8 people. These guys, the first floor is full, the second floor, these are all full. This one is full, it's just smaller. So this one's really happy with 2 electrons, these guys are real happy with 8. Yes?
So outer configuration just means that for valence electrons?
The outer configuration would be the valence electrons, yeah. So the number of valence electrons for any main group element except helium is the group number of its column. And the row number, the period number, tells us the highest principal shell. So if it's in period 3, the highest principal shell where the valence electrons are is 3. I forget why I put that there. Maybe, yeah, I don't know. Anyway, there it is again. The transition series. The transition series represents filling of core electrons, not valence electrons. And so the number of valence electrons is mostly constant throughout there. There's 2 exceptions that are things that are weird. So let's look at that. So potassium has 1 valence electron. Calcium has 2 valence electrons. When we go to scandium, it has 4s2, and then the next electron that's going in goes into a d orbital, but it's the 3d orbital. That's not the highest floor in the hotel. That's the next to the highest, but it's not the highest. Valence electrons are the ones on the highest floor. So that 3d1, that's not a valence electron. This one has 2 valence electrons. We go over to titanium, we're adding another 3d electron. Still has 2 valence electrons. Vanadium, 2 valence electrons. Chromium and copper are weird. There are other ones, but you're not responsible for them. So here's chromium, and here's copper. The others are fine. 4s2, 3d5, 4s2, 3d6. We're just adding in the d's, skip that for now, 4s2, 3d10. Okay, so zinc, nickel, cobalt, iron, manganese, vanadium, titanium, and scandium all have 2 valence electrons. Chromium and copper are weird. Why are they weird? Well, let's see if we have space somewhere to look at this. So here is an orbital diagram. I'm just going to do the things above argon. So there's 4s, and then there would be this 3d. And so as we're filling in electrons, so this is going to fill up first. And now here's scandium. It's going to put 1 electron here. It makes sense. The next electron that titanium's going to have would go in here. And then for vanadium, goes in here. And for chromium, what do we expect? We expect that you'd put an electron there, right? We would expect that it's 4s2, 3d4, but it isn't. What happens? Let's see if I can do this without destroying everything. This electron moves over. Do you see the symmetry in that? These two subshells, these two rooms in the hotel are both half full. It's one of those odd bonuses. You know, if you buy 2 packages of this and one of that and one of those, and you jump on your left leg and sing happy birthday, you get a discount. That's lower in energy. And so that's what chromium does. And manganese, I'll put this electron back in there. 4s2, 3d5. This is kind of symmetrical too. We've got a full and a half full. So that's kind of nice. Then for iron, these guys are going to have to pair up. So there's iron, there's cobalt, there's nickel. For copper, we expect it to be like this. But what actually happens, we've got this guy from the 4s that moves up again. This is what copper does. So this is the 4s being half full and the 3d being completely full. There's a bonus for that too. And then for zinc, we fill in over here. So chromium and copper are weird. If you're just trying to pass the class, you'll be just fine forgetting all of that, just about the chromium and the copper. If you're an A student, if you're going to go on to Chem 1A, you should try to get a grasp on why chromium and copper are weird. Any questions? Yes?
Okay, I'm kind of lost. The transition elements, the valence electrons is the rho minus 1, but I don't get what you were saying.
The valence electrons is not the rho minus 1. The D block is the rho minus 1. So they're filling in the 3D subshell, but these are not valence electrons, even though they were added after 4s. The valence electrons are the ones with the highest principal quantum number, the highest shell. So only the electrons in the 4th shell are valence electrons. These are not valence electrons.
Okay, but chromium and copper are...
Chromium and copper do weird things because they bump one of the 4s electrons into the 3d to make things either half-filled or completely filled. That's why we say the number of valence electrons for the transition elements is relatively constant. Most of them have 2, but some of them have 1.
So is the highest energy still in the 4th level, or the 4th floor, or would it be the 3D?
The 3D subshell is higher in energy than the 4s, but it's not considered valence electrons. Valence electrons is not necessarily the highest energy. It's the highest shell number. So here's just another illustration of how do we find an electron configuration from the periodic table. I probably should have put this one way back at the beginning. So for phosphorus, doing the noble gas. Well, find the noble gas that comes before phosphorus. So it's at the end of the previous row. So there's neon. So we've got neon in parentheses, in brackets, sorry. And then after neon, here's the third. We're going through the S block, 3s2. And here's 3p, 1, 2, 3. 3s2, 3p3. Any questions? What what if, let's pick something different. Let's try, what's right here? Tellurium. So, how would we do tellurium? Well, we need to know what this is, right? That's krypton. So doing tellurium, we would have krypton. And then after krypton, 5s2, right there. Yep. And then going through here is 4d10. And then next up will be over here, 5p4. Yes?
So the valence for that would be 6, correct?
It would be 6. Yeah. The valence electrons would be the 5s2 and the 5p4. The 4d10 are not valence electrons. And if you get mixed up on that on an exam, the other way we can tell how many valence electrons tellurium has is because it's in group 6a. Okay? And if you count those, it's not going to be 6, it's going to be 16. But these guys are not valence electrons, ever. The Ds are not valence electrons because they're always lower. I'm sorry, they're always lower than the S that comes right before them. So I try in my slides to give you sort of sets of instructions, like when we were doing empirical formulas. Some of you were just kind of completely forgetting what the next step was, going off and doing creative things, which is not valued in situations like that. When you're not sure what you're doing, go look for the slide that has the set of instructions. So this is the set of instructions. Writing an electron configuration for any element based on its position in the periodic table. Represent the inner configuration with the symbol for the previous noble gas in brackets. The outer electrons are determined from the element's position in a particular block. The highest principal quantum number equals the row. The principal quantum number of the outermost d electrons equals the row number minus 1. Now, you may go refer to those instructions and say, well, that didn't help me at all. Then text me. So let's do another example. Use the periodic table to determine the electron configuration for tin. Well, first we have to find tin. It's element number 50. It's right here. So what's the previous noble gas? Krypton. And then, so there's krypton, and then after krypton, we've got 5s2, 4d10, 5p2. So this is filling up 5s2, and this is 4d10, and 5p2.
5p2 would be the valence electron.
The 5p and the 5s. So it's got 4 valence electrons. And for the exam, I'll give you a periodic table. It won't be color-coded like this, and it's not going to have these little electron configurations there. But you can write on it. Yeah? And so you can, if you want to bring colored pencils and quickly color in your periodic table, that's fine. So S, P, D, and F. There could be a question that asks, well, how many electrons could there be in the 5F subshell? The most you can fit in F on any level is 14. And if you don't remember the number, you can count the columns, and there you go. There's the 14, there's 10, there's 6, and 2. It's all hiding in there.